Hello.
Hello, hello.
How are we all doing? Let me just see who I've got. Joshua, Anton, Celine, Jihang, and Mantilla. Hello, everyone. Thanks for joining.
Hello.
I am down here at the creator space at the moment, where me and a few WattHack guys are just processing some e-waste for you for Thursday, Friday at the moment. So yeah, it's going to be a good couple of days. We're all very excited. So yeah, this is just going to be start off as a bit of an info session, answering a few questions, giving a general overview of the event to get you guys prepped, some look at some of the e-waste stuff that I've managed to strip so far. And you can get your creative hackathon juices flowing and thinking about what you might want to do. And then probably at about 3:30 or so, we're going to kick into Arduino Crashcourse for anyone who needs to get up to speed on Arduinos, because they're going to form the sort of the brains of the operations in most cases, I imagine. So can I just get a quick indication on who was planning on just hanging around for the information and then taking off when we kick into Arduino, or was everyone going to be hanging around for the whole thing?
I was just around for info.
Just for the info? Yeah, no worries. All right, well, yeah, we should have a bit of a split then. And yeah, this will be recorded. I've had a bit of interest in some people who won't be able to make it to this virtual session. So I'll also be recording this and uploading onto the WattHack YouTube page as soon as I can. So you can always come back and have a look at what you missed. But if you've done Arduino 101 or 102 with us, this is going to be a bit of a condensed version of that. So yeah, let's get into it. Let me know if it's reasonably quiet here at the moment, but I believe that there's going to be some inductions kicking off soonish. So if at any point it gets too loud in the background noise, let me know. And yeah, it's a little bit hard to hear some of the audio coming back my way. So apologies for any audio issues in advance. Okay, and I am also reasonably ill prepared for this as well. So forgive any hiccups. I hope you've all been enjoying your break, or if you're taking any winter subjects as well, that they're going okay. All right, so I'm just going to pull up the run sheet from that I've been provided. First time I'll be seeing it. But yeah, in general, if you haven't heard, WattHack is our first club's hardware style hackathon. And the aim of it is to basically claim back some e-waste and process e-waste and get some useful and fun projects from yeah, electronic waste. Because as you know, there's been a bunch of you know, electronics just get thrown out, and there's a lot of waste and a lot of you know, components that can potentially be used for fun projects. So it's run over 2 days, this Thursday and Friday. On the first day, we'll be kicking off from 9 a.m. So a lot of the first part of the day will be inductions into the creator space, because that's where at base we need to make sure we meet their HSE requirements. So we need to be, you guys will be getting the general induction, which will translate to use of some basic tools and the facilities and all that sort of stuff. Unfortunately, I don't think, or no, maybe there is. I won't say anything on that. I think there's some basics electronics inductions for you guys, bar soldering potentially. So the potential for soldering and desoldering components does exist. Whether you'll be able to do them yourselves, I don't think you'll be able to, but certainly on the MUEC team, we'll be able to help you out with any soldering on the day. There will be effectively 1 meal provided per day. They're quite long days. Our first one starts at 9 and sort of from through till we've got 7 p.m. on the run sheet on the first day, and then the second day is 10 a.m. till 5 p.m. So they're reasonably long days. One meal will be provided, but that won't necessarily take care of all of your eating needs. So obviously, if you don't know where the creator space is, it's just opposite stop 1, basically on the Parkville campus, diagonally opposite the KFC. On that side, so you're in around all the uni stuff and all that, so you shouldn't go wanting for things to get a hold of. So yeah, inductions, and then through to planning, which we'll talk about a little bit towards the end, planning projects and things like that. And there's going to be some industry people there. Hey, Alex. Who's our industry peeps? Who have we got?
We have, do you want me to get on the screen?
This is Alex, everyone. If you haven't met Alex before.
We have representatives, they can hear me, I guess.
I'm not sure, I'll translate information.
We have representatives from CSIRO and Defence Force.
Yeah, so reps from CSIRO and Defence Australia.
And they'll sort of be hanging around helping people, figure out their projects and like that.
Yeah, so they'll be wandering around helping you through the various stages of your projects, and yeah, the judging will be part between MUEC and industry reps as well. There will be some rubric that we'll share with you on the day as for the judging, but yeah, generally we're not looking for technical capability or technical advancement and things like that. So whatever your skill level is, there's certainly a place for you, and there's a place to do well and have fun and potentially win one of our prizes, which are cash prizes. So we'll release details for that on the day, but certainly the first 2 or 3 winners will be have a cash prize for that. So yeah, there's a little bit at stake and should be a fair bit of fun. Any general questions that I can field from you guys? I know that wasn't the most exciting information, or maybe it was, but yeah, hit me up with any questions that you may have and I'll do my best to answer. I've got Alex here somewhere and some other people, so we can, yeah, certainly sort you out if you've got any questions. Doesn't seem like
do you have any idea when we'll find out about our teams, if we haven't got like a full-size team yet?
Yes, okay, good question. Probably in the morning session. Let me confirm again with the master of WattHack. Alex, when you're ready again. Teams for those who didn't allocate a team in the sign-up sheet. Will that be sorted on the day?
On the day.
Yeah, on the day. So you.
Just because numbers are
Yeah.
moving around a bit.
Yeah. So you'll be assigned. I think it's 3 to 5. We're shooting for.
If we build groups, it will be maximum 4.
Maximum 4.
3 or 4.
Yeah. So yeah, if you're going to be in an assigned group, it'll be a maximum of 4. But you'll find out about that on the day, on the morning. Yeah. Cool. Anything else? Any other general housekeeping questions for anyone? Otherwise, I'll take you over and we'll have a look at some of the electronics processing that's going on. Cool.
Sounds good.
Has anyone managed to make it down to the creative space yet?
Yeah, I have.
Yeah, what do you think? It's nice.
Yeah, it's very nice.
So yeah, yesterday I was out at A Tech Recyclers down in Mentone and scouring through their yard for various electronic equipment, and came back with a carload that we've been processing yesterday. So we'll come over and see what Tom Harper's got going on. Looks like he's halfway through dismantling a printer. What sort of components are you getting from the printer, Tom?
Oh, there's lots of fun things. Oh, actually, for a random tangent.
Just hold on a second. Can you guys hear when Tom speaks? Or not really?
Yeah, we can.
Yeah, all right. Just speak loudly, Tom.
All right, one of the coolest things I found so far was this wonderful little, I don't know how it's going to come up, fractal antenna, which I thought was an absolute ripper. But beyond that, there's heaps of stepper motors and wonderful little bits and pieces. Oh, what might be useful? Some nice photo interrupters. So, transmitter, receiver, and when there's something in the gap, and some nice little headers to access it. Beyond that?
Ink.
Oh yeah, ink.
Ink everywhere.
Yeah, it didn't end up on the table.
Yeah, so we've been processing lots of printers. I picked up about 8 printers. So printers are an excellent source of stepper motors. Yeah, a lot of them are multifunction printers. So they've got the scanning component. So optical encoders for keeping track of like shaft positions, lenses for the scanning portions, things like that. We've got lots of belt drives to go along with the steppers, keypads. Obviously we're pulling out lots of just general circuit boards. These are of limited use. Potentially you can reclaim some, switches and things, but a lot of this, surface mount stuff is not going to be too much of use. We will be providing passive components, so resistors, capacitors, things like that are be easily breadboardable as needed. So we're not necessarily going to be reclaiming those. We will where we can, but not 100% the easiest way to go about it, at least for hackathon. We're learning a lot about what actually goes into making these sort of devices. Some are a lot easier to pull apart than others. Lots of plastic clips and hacking at it with pairs of pliers to actually get stuff coming apart. Alex is working on another printer. Looks like you've got that one looks like the power supply portion. So we'll be keeping you away from anything mains. We're strictly logic level for the hackathon, or, sort of up to about 50 volts. We don't want to be going over 50 volts with anything for sure. So yeah, depending on what we get, particularly with Arduinos and stuff, that's where we're playing with anyway. This is our sort of box from some other stuff that we did. So again, some nice, can't see that, some motors. That one's got an encoder on the back. There's some solenoids, more steppers, lenses, keyboards, LCD screens with capacitive touch buttons, heat sinks. There's plenty of PC fans that we've got, hard drives. Don't know what we'll get from hard drives. I don't think we pulled one apart yet, but potentially some motors and platters or something like that. Got another printer coming apart over here. It looks like we're not too far into this one. A lot of the plastic outers come off. Yeah.
Trying to figure out how to get in.
Yeah. As I said, some are easier than others. But yeah, printer's good source of steppers and motors and things like that. And then on top of that stuff, you'll have your usual Arduino things to play with. Yeah, there's some shafts, a lot of gears, plastic gears coming out of the printer, mechanical functions and things like that. And there's no particular theme for what the builds and projects need to be. So yeah, it's time to start getting your just get that thinking cap on a little bit, having a think about what you can do. And then, as I said, the judging component and the criteria is not necessarily about how, you know, how much of a final product you can make or how useful it is or anything like that. We just want to see some creativity come through. Could be you know, like a mechanical art piece, or, you know, could be something that's got some bit of functionality to it, like driving motors for, you know, making a small robot or something like that. But, you know, the sky's the limit. And just making use of some of these reclaim components is the goal. And yeah, we're doing most of the stripping out for you guys, but you'll be able to have a look at some of the broader level stuff that we've sort of left more whole. You can have a look at it and be like, oh, I could really use that, or I could really use that, and we can help you get stuck in and get out what you need from that as well. Yes, I think I'll open up the floor again for any more questions. I'm just trying to remember the schedule that I put forth, but I think I don't have too much to talk about in terms of WattHack general info, and I'll think about kicking over into Arduino a little bit as well. Yeah. Awesome. So I'll take 5 minutes to get my Arduino stuff set up. Yeah, 5 or 10 minutes. It's 20 past now. I'll stay on schedule, and we'll kick off Arduino 101 at 3:30. But before I do that, since you're at home, those of you who are sticking around will want to sign up for Tinkercad and get an account going for Tinkercad. So I'll share a link for that, so you can join up for that if you need to. Because yeah, if you don't have Arduinos at home, or maybe you do, yeah, getting stuck into Arduino, we don't want to put up any barriers. Obviously, you'll be working with actual hardware on the day, but Tinkercad's a good online Arduino simulator, so you can get started with that. So I just shared a link in the chat. I'm going to go on mute and off video for 10 minutes or so, and we will join back in at 3:30 for the Arduino crash course. And yeah, thanks for joining so far for the general info. If you're going to stick around, I'll see you in 10 minutes. If you're taking off, thanks a lot, and I'll see you on Thursday morning.
Cheers.
Thanks everyone. Okie dokie. Everyone here? So yeah, hopefully you have been able to sign up to Tinkercad, get an account going there. You can just use the free stuff. There's no class or anything associated with that. So you just create an account with an email address to get access. I'll be mostly doing the stuff on Tinkercad, I think, because that'll be easier. But I've also got hardware here to show you guys to be a little bit closer to what you'll be dealing with on the day. But Tinkercad's a pretty good option to play around with, at least in the meantime. I shared some slides and PDFs links in the chat, so please download those. I suspect, because this is just a crash course, if you do want to get really up to speed before the event, that you take the time to go through the slides and do everything in full, because we certainly won't have a chance to today. We're cramming in about 4 hours worth of content into an hour and a half. So yeah, I definitely suggest you do that. Okay, so let's get started. Does anyone here have any experience with Arduino? Anyone played it or have any or are we all starting from scratch?
Yeah, first time for me.
Cool. A little bit from Jing. Awesome. Okay. So yeah, basically, so this, where's my camera? This is an Arduino. This is called an Arduino Uno. So there's a few different types and models of Arduinos. This one's called the Uno. There's like a Nano, and yeah, a few others like that. But this is the Uno. Sometimes they'll be legitimate, but the design is open source. So there's a bunch of knockoffs per se of the design of Arduino boards. And the brains of it is a microcontroller chip, AT-Mega32, I believe. And the rest of it is peripherals. You've got some GPIO pins on headers here that you can plug basic components into. A USB port for interfacing with your computer, a barrel jack for power supply. You can also run it off USB power, depending on what your use case is, and various other peripherals and connectors. So this is the brains of the operation. This is the thing that we're going to be programming in code, and then also uploading the code to this, which gives it the instructions, and then this can become the brains of the operation by doing certain things with the GPIO pins, like writing them to high or low voltage in terms of logic level, so 0 or 5 volts, so you can control LEDs, motors, and things like that. So this guy really does form where all the thinking happens. We'll also be prototyping on a breadboard. So this is where you can make electrical connections on this. So this is very handy for quickly prototyping up electrical circuits without the need for soldering. So you can just plug in the connections directly into the holes, if you can see those there. So there's a few little things to be aware of with the breadboards. And I will just say that oftentimes, if I just share my screen, share screen, that one, share. So oftentimes schematics and circuit schematics will be shown with this sort of form. So obviously this is the breadboard, and here is the Arduino, and with wires shown as colored lines. So the thing to be aware with on breadboards is where actually are the electrical connections being made. So if we have a look on the sides of the breadboard, and this is also on the real life breadboard as well, these the very outermost and the second most outermost connections are called the rails. So this would be referred to as the negative rail or the ground rail. And this red one here is the positive or like VCC rail here. And all of these holes along this way, along the rails, are electrically connected. So anything that runs all the way along in this direction, along each of those rows is electrically connected. So the blacks are all electrically connected along here and the reds are all electrically connected along here. So any component that we plug in is going to be connected to each other. Same thing for these rails down here. That's in contrast to the connection points in the middle of the breadboard. So the connections for these run across this way. Okay, so row number 1 here is electrically connected between F, G, H, I, and J. Row 2 is all electrically connected for F, G, H, I, and J, but it's not connected to row 1. So all of these are connected this way. There's no connection across the center of a breadboard, and then all of these rows over this side are connected along the numbers. So A, B, C, D, and E are all connected as well. So you really need to know how a breadboard works to make an electrical circuit. They're quite simple, but yeah, just remember the rails on the edge are connected along the length of the breadboard, but across the center are connected across each half along the numbers. So hopefully that's clear. Any questions about breadboards?
Are the rails at the top and the bottom connected at all?
No, so they're separate. So only between this black negative rail at the top, but that is not connected to the one along the bottom here.
Yeah.
So typically, yeah, that's where we connect our ground and where we connect our like +5 volts or something like that. You don't need to, but that's just convention. It makes it easier for us. Okie dokie. So then from there, basically, when you're asked to make a circuit, you can either start with the hardware or the software. You sort of need to do them a little bit at the same time. But we're going to start with this first example from Arduino 101, which is 2.2 digital write, and start to make this circuit here. So I'll make it in both. I'll make it in hardware and in the Tinkercad. The other thing that you'll want to do though is download the Arduino development environment. So it's just an app for Windows, Linux, and Mac. And that's what you use to write your Arduino code in and interface with the board. So that the Tinkercad works all online. So you don't need the Arduino app for that, but you will need it come Thursday when you're actually using the hardware. So I'll quickly find the link for you guys there, but you should be able to find it when you just type in Arduino. Arduino. And yeah, the Arduino IDE. I think this should be the latest version. Yeah, so I will share that in the chat. So you want to go ahead and download that, making sure that you've got it ready for Thursday. But we'll start with Tinkercad. So you guys can follow along with this. So in Tinkercad, once you've signed in, it should look something like this. Let me know if it's vastly different. And there's a few different sort of sub areas that Tinkercad offers you. We want the circuits area. So you click on circuits here and then click on create new circuit. And it should bring up a sort of a blank canvas for you to start working on. So if we're going to be making this circuit here from 2.2, we need to obviously add, we'll start with the hardware. We need to add an Arduino component and we need to add a breadboard component, are the two main ones, and then smaller things from there. So we can search in our components. We can just search for Arduino. So we've got a few options here. So we've got Arduino by itself. We've got Arduino and a breadboard, which will be potentially a good one to use. But there's a bunch of different examples and starters that you got there. But I might go from scratch, and I might start with just the Arduino. So you can click on it and drag it over into your workspace. And that gives you basically a virtual version of the board that I've got in front of us here. So it should look pretty similar. And then we also need a breadboard. Oops. I don't use Tinkercad that often, so please bear with me while I deal with components and get these chat windows out of the way. There we go. Breadboard. And we added a breadboard on there. Oops. Okay. For some reason that's gone and rotated. I don't really want that to be rotated. But what can you do? Okay, so we're going ahead and making the this circuit here. So basically our aim for this is to blink an LED. So we need an LED on our circuit. So hopefully you recognize some basic electronic components. So this is an LED, this is a resistor, and basically an LED will glow when we have when it has current passing through it. So I'm assuming we've all got some basic electronics fundamentals, but if you do have any questions, please stop and let me know. Effectively, all we're going to do for now is copy this circuit onto our own breadboarding component. So LED, there's one. So I can drag that. We don't need to exactly follow what the thing is going, but if you want to troubleshoot, that might be worth it. But I know I can place it like this, and that's a good start. The other thing that we need to place is a, resistor. There's one there in my common components. And if we have a look at where this needs to be placed, we place it in the same row as one of the legs of the LED, and the other one goes down to our ground rail. Okay, so going from one of the resistor, one of the LED legs down to the ground rail. So same thing here, one of the LED legs down to the ground rail. Perfect. Okay, and now bring my weirdly rotated Arduino over here. We can start making some connections. So just having a quick look at the pins on the Arduino. We've got the GPIO pins up here, or the digital pins, 0, 1, 2, 3, all the way through 13. We've got a ground. We've got a pin called AREF. Down here, we've got analog input pins, A0 through A5, and a few more utility pins down here. So grounds, 5 volts, 3.3 volts, VIN, reset, IOREF, and things like that. And they're pretty much the same on the actual hardware board. So what we need to do is start making connections between the Arduino and the breadboard. So I'm going to make a ground connection, and I can choose any one of these ground pins available on the Arduino. I'm going to just use this one and hook that up to my ground rail, okay, which is the black negative rail that the resistor is plugged into. it's not used in this one, but it's also appropriate to connect the 5 volts up to the positive red rail. Okay, so it's not actually used. If we have a look at this circuit, you can see that even though it's connected to this rail here, there's nothing connected to it and nothing special happening on that rail. So it's just sitting there, it's just connected as good practice. And the other thing we need to do is connect a wire from the anode side of our LED. So that's the kicked out side, the non-flat side, to pin one of our digital pins. And in this case, we've got it going to pin 3. Talk more about pin choice in a little bit. So connecting that up to pin number 3. Okay, so there is the hardware side of our circuit that we need to build. Everyone managed to follow along with that so far? Any issues? Can't figure out how to bring up the anything. So yeah, had 1 thumbs up there. Thanks, Anton. Awesome. All right, so I'll keep going on and we'll start to talk about the software because this is the hardware sorted out. So the software part of it is down below. So Arduino works with software and hardware in tandem. We program the chip on the Arduino to do things. I'm just going to scroll up a bit and talk about the most basic program here. And this is the, so 2.1, this is the simple Arduino software boilerplate code that we always need to have. And there's 2 main functions here. And Arduino code is sort of a subset of C++. So if you've done any C++ or C-like programming, that's the general gist of the language. So yeah, hopefully you've done some sort of programming before. Even a bit of Python will probably help you out. But yeah, Arduino is firmly in the C++ programming language, but it is a subset of it. And there's 2 main functions that we have. There's the setup function and there's the loop function. And once we program and turn on the Arduino chip, 2 things happen. The first thing is the code in the setup function gets run once. And once that's been run once, we go and the loop function will continuously run until we either hit the reset button or power gets turned off to the Arduino. So that's what happens. The setup code runs once, and then the loop function runs continuously over and over and over again as fast as it can until we reset or power gets cut. So that's the general framework that we have to think about when we're making Arduino programs is what do we need to set up, and then what loop do we want to run? What's our main loop that will just keep running and running and running? So the task for this particular exercise is to blink an LED. So to blink an LED, what do we need to do? We need to turn it on and off. So the job of the Arduino is to basically turn on this pin number 3, basically put voltage to that pin and then turn the voltage off. Put voltage to that pin and then turn the voltage off. So when pin 3 goes high, we say, so when pin 3 goes high to 5 volts, current is going to flow through the anode of the LED, down through the resistor and to ground. And when current flows through the LED, then it's going to light up. When we put pin number 3 low, so down to our ground voltage, obviously these are at the same potential and no current is going to flow and it'll be off. So if we alternate these 2 states, that forms the basis of our loop function, and that's going to make sure we blink our LED. And let's inspect the code a little bit. So we need to declare some variables. So we need to define the pin number that the LED is on. So we see int LED equals 3, and the comment is the LED is connected to pin 3. So that number here corresponds to the pin number that we've connected our LED to, the one that we have control over. In our setup code, we're doing one thing. All we're doing, we're turning the pin mode for the LED. So remember, LED is a variable. It's this one here. So LED is the number 3. Pin mode for pin 3 is an output pin. So that means pin 3 is going to be driving. It's going to be, we have control over it. We're not going to be reading from it. We're going to be driving the state of that pin. So we're setting the pin mode of pin 3 in our setup. And remember, this gets run once. It only needs to be run once for our program. Then we come down to the loop. So this will get run over and over and over again. First thing that we do on line 10, we digital write is the function that we call the LED pin. So that's number 3. So we're writing pin 3 to go into the high state. So output high, 5 volts. So that's when our LED is going to be on. Then we need to delay 1000. So the delay function is in milliseconds. So 1000 milliseconds, that's 1 second. So our LED is going to be on for 1 second. And then we drop into the digital write for the LED pin going low. So 0 volts. This should read output low, not output high. That's a typo in the comment there. And that's going to be off and delay for another 1000 milliseconds. So 1 second. And then back to the top. We go high, wait a second, low, wait a second, high, wait a second, low, wait a second. So that's going to blink our LED. All right, let's quickly bash this into our simulator. And to that, you can click on the code button and just make sure when you drop this down, make sure you set it to text. You don't want to be dealing with blocks. You want to be dealing with the text version of the code editing. You can see it has given us or it's at least given me some boilerplate here, which is not necessarily what I want. I'm going to declare my LED to be pin 3. LED is an output. LED, change that to LED. So we could put this LED on any pin that we wanted to. We've got 13 pins to play with here. Pins 0 and 1 are sort of used for different purposes. So if you can, we generally avoid 0 and 1 unless we have to, because there can be some unexplained behavior sometimes if we use those and aren't careful. So generally 2 and up. So if I've done this correctly, I should be able to run this code by starting the simulation. And we can observe in our code simulator, our LED is indeed blinking on and off once every second. So it's on for 1 second and then off for 1 second. Good. And I can stop the simulation. All right, so that is the basics of a very first Hello World project for Arduino. Did everyone manage to get that going? Anyone have any particular troubles? Please let me know. Awesome, good work, Anton. Excellent work, Jing. Good work, guys. Good work, Daniel. Good work, Haflan. Okay. So does anyone particularly want me to do up a hardware in-person version? Hopefully the Tinkercad is enough to get you off the ground. Obviously on Thursday, you'll have the hardware to play with specifically, but I think Tinkercad's pretty good. And yeah, hopefully it covers all your needs. I can do it if you really, really want me to, but otherwise we'll make the best use of our time just by soldering on through. The one thing to watch out with LEDs, guys, is they are polarity sensitive. So I'll see if I can find one for in person, but you'll notice in Tinkercad, they are slightly different shape. We'll have a look at how that corresponds to the polarity and how you need to make sure you connect them in person. So give us a second. Okay, just going to stop the share for a second, and hopefully that means that you can get the big picture. So here is an LED, which you'll probably have a lot of different options for using these on the day. This one's a red one. They obviously come in many different colors, but generally they all work in a similar fashion. But they, as I said, they are polarity sensitive. So that means we need to make sure we connect them to our voltage source in the right way. So they have what's called an anode and a cathode, which is a positive and a negative side. That anode being the side that we need to connect to the positive side, or the high potential side of our circuit. So how do we know which is which? There's two different ways. One way is, I'll see if we can see there. So if you can see, there's legs that have two different lengths. One's a long leg and one is a short leg. And that can help us to tell which is the correct polarity for the LED. The short leg is the cathode and the side that we need to connect to the negative side, and the long leg is the side that we need to connect to the higher potential, the positive potential. But with a lot of our reclaimed components, you're not going to have access to the full legs. They'll be trimmed or cut or something like that. So we need alternative ways. And one of the ways, this might be hard to see, if you can sort of see there, one side of the LED, sorry, this is really hard to organize with the camera. One side of the base, so if we're looking from the top, one side is round and the other side has a bit of a flat spot to it. Hopefully you can sort of see that flat spot. And the flat spot is the side that corresponds to the cathode and is the negative side. So look for the flat spot on an LED and that will tell you which is the negative side. Okay, and that is sort of shown in the Tinkercad version. You can see that the left-hand side of the LED is the negative side, of the side that needs to be on the lower potential. Okay, that is 4 o'clock. Let me just see where we're up to. I'm going to skip over the button. You can have a try at getting this button up, this button example up and running, but basically this is an example of reading the state of a digital pin. So we're using pin 4 in this case to read the state of the button. And just looking at the circuit, we can see that this side of the button is connected via a resistor to our VCC 5 volts. And then there goes our input pin to pin 4. And then our button, when we press it down, it makes a connection between here and here. And then that goes down to ground. So when our button is not pressed, what is the point at this node of the circuit? When the button's not pressed, well, it's getting 5 volts. Okay, because it's connected to here and there's no current flowing. So this point must be 5 volts. So if the button's not pressed, and we read in the state of pin number 4, it should be reading high or 5 volts. When we press the button basically is a short. So the button, and at this point will go low, it will go to our ground potential. So when the button's pressed, this will go low, and pin 4, if we read the state, it will be in the low position as well. So if you have a look at the code, that should be, you should be able to figure out that when the button is, button state is high or 1, we write the lead low, or every other time we write the lead high. So depending on exactly how this is set up, you can try it yourself. The button will control the LED. It's either going to be on by default and turned off when you press the button, or off by default and turned on when you press the button. And we can have control over all that in using the software. Also some code logic here with an if and else as well. Okay. Let's have a quick talk about potentiometers and serial communication. Okay, so this is a potentiometer. That's what it looks like in Tinkercad. This is a potentiometer for the purposes of hardware and what it's going to look like. So basically, there's a shank or a shaft that can be turned, and three pins, three legs, the three-terminal device. We can get the value. This one's 10K pot, we would say. And basically, we use a pot typically. It can be used in two main ways. One is as a variable resistor, but usually we're going to use it as a voltage divider. So as we can see from the schematic here, we hook up one of the outermost pins to ground, one of the outermost pins to VCC, and then the signal pin is the middle pin. And as we change the position of the shaft, that's going to change the voltage that appears on the middle pin, on the signal pin. So that will vary between ground and 5 volts in this case as we turn this. They can be plugged into breadboards. So the pins are in such a way that you can just plug them straight in. You just got to press them in, and then you can make connections on the breadboard as you need to those different pins. You'll also find some potentiometers on some of the reclaim components that we've got as well. They don't always look similar to this. Sometimes they're a bit smaller and have slightly different functionalities, but they're there. So let's have a try at coding and making this schematic up here with the potentiometer. And we'll see what happens there. And if someone's feeling brave, maybe we can get you to showcase by virtue of sharing your screen and walk us through what you've got. Otherwise, I'll start making it now. So just following example number 2.4. Okay. And just sing out if you've got any questions, guys. So potentiometer, no matter where. Connect one of the sides to ground. Oops. Connect one of the sides to VCC. So just remembering our breadboard connection rules. And then I'm going to connect the middle pin, the signal pin, to one of my analog read pins. So the analog pins on an Arduino, they are able to read a voltage between low and high. So low and high on an Arduino is between 0 volts and 5 volts. So they will essentially read in, they won't read in the voltage directly, but they'll read in a integer value that is proportional to the voltage. I forget what bit depth it is, but I think it's between 0 and 1023 in terms of the numbers. So that number will scale depending on what the voltage is. Whoops, deleted that, didn't want to. So A0. Okie dokie. And let's have a look at our code. Let me also just add in the button as well. I don't remember whether we use the button particularly, but I'll add it in just so I'm up to speed. So button and a resistor. Button bridges the gap. I'm going to go one side. Let's go just to make sure I'm doing the same thing. Yeah, between there and high. There to low. And that coming over to pin. Okay. Nope, they added on pin 4, but that's fine too. And having a look at the code. So I've done button is 2 here because I've connected it to pin 2. So there's a good example of, you know, it doesn't really matter which pin you connect it to. We need a variable for the button state, which we're going to call integer. We don't need to initialize that. We need a value as an integer and then a mob connection as well. I'm going to call mine pot value, just to be a bit clear. We're initializing that one to 0, and then int pot connection a 0. Okay, and some setup code. LED is still an output, button is an input, and we've got this new one called serial.begin 9600. So serial is the USB communication. So this is a way that you can get the Arduino board to communicate with your computers via serial, so via the USB. And that can be handy for debugging, as we'll see, because it can print out values. Okay, so I've got to set my button mode to input. Pin mode, button, input. And serial.begin 9600. And that's called the baud rate, how fast the communication happens. Okay, and in our loop, we have, what are we doing? We're doing a read, analog read from the knob pin, which was A0. So we're going to read in the value. Well, we're going to read in what current voltage level as an integer. Remember, it's scaled as an integer. Is the A0 pin, because that was our definition, is the A0 pin. So value equals analog read pot connection. I think that was it. Yep. Do a serial dot print. We print out the sensor value, and then so notice the difference between print and print line. One does a new line character at the end, so these are spaces in here as well. So serial.print sensor, oh, can't spell, sensor value, serial.print line, and then I'm going to print out value. So whatever's stored in value there. We read in the button state. The digital read. Yep, digital read button. So that's reading what is going on at pin 2. We've got a logic block if, what do we have? If button state equals 1, put the LED low. Remember double equals for logical comparisons. Then we're doing, we'll just sneak this one in. We had LED low. And then else think. I don't do too much C coding, so sometimes my syntax is a bit off. Else did drill right led high. And then we just delayed by 5. Okay, so I'm just deleting the comments, but it's always good practice to comment your code just to make sure that everyone else knows what's going on. Okay, so let's see if I've got any mistakes. I probably do. I can go start. And you can see that it's got some errors here. So let's just have a look. It's always good to take note of what errors you've got so you can debug them. Let's just have a look here. So it's got this one here. So I've accidentally written height instead of high. Let's see if that was all. Value was not declared in this scope. Value. Yeah. So here's an example. So I'm trying to do stuff with this variable called value, but I haven't declared it anywhere. So I called mine pot value instead. So instead of value here, I need to call it pot value. And instead of value here, I need to call it pot value. Okay, so that should be happier. I've declared it up the top. Let's see. Okay, so the simulation is running. I can see what happens when I press my button. So my button is turning my LED on and off, which hopefully is understandable from the code. But what about this serial print and the pot value? What's going on there? So what you can do is open up in Tinkercad the serial monitor and see what's going on. So you can see there's some values being printed out down the bottom here. They're all zeros at the moment, but let's have a look what happens when I change the position of my potentiometer. Okay, so at a position, we start getting different values. So 0, and let's see if we can go all the way through. What's the high one? Yep, so when it's at the maximum, we start reading 1023, which is the maximum that the analog pins will read in when the voltage is 5 volts. So there would be 5 volts going to pin A0 here. So there's an example of what the potentiometer is doing. It's changing the voltage value on the wiper pin. They're calling it here, or the signal pin, depending on how you're using it. And we're reading that in the Arduino and can do various things in it with software. So is the value bigger than this or less than this? We can do certain things, driving pins high, low, turning off things, getting them to do whatnot, etc. Okay, what else was in 101? Some servos. Let me just check the chat. Yep, good work, Jing. Picking up on the pot value there. Excellent work. Good. Any other questions at this stage? Did everyone get that one working? Anyone want to share? I mean, I basically have. Anything not making sense? Excellent. Okay, so it is 1:15 now. I'm probably going to spend a bit of time talking about motors. So servo motors towards the end of this one, we'll have a play with. And I'll just have a breeze over 202 as well. I think this was more of a specific project-y type one for 202. We use a ultrasonic distance sensor and a servo motor for that one as well. So probably, yeah, we'll have a look at servo motors, and probably the motor drivers that we've got access to. And that'll be the best sort of setup for Thursday. We'll probably have access to the various components that we've got, such as the ultrasonic sensor, which measures distance via a basically like an echolocation style ping, which you could probably use in a project if you want to, but they have been reclaimed, obviously, which we want to minimize usage of. Alrighty, so let's have a look at servos. I'll just see if I can grab one. It's all good. How far? It's fine. Okay, so I've been informed that the servo motors have been put away. So we will make do. We can have a look at one in Tinkercad. And we'll just have a look for, stop that simulation, servo, so micro servo, and place that down. So basically a servo motor, there's two types. Mostly we're going to be, so there's a positional here and continuous. We have both types. So be aware that a positional servo motor works slightly differently than a continuous rotation servo. So positional servo, what you do, you specify at what angle you want it to go through. So typically they have a range of about 180 degrees. So the yoke, which is this part here, which sits on the shaft, can sit at any particular angle between 0 and 180 degrees. And we basically tell it in software, go to this angle, go to this angle. And we can do that, you know, with various updating frequencies so that it will look like it turns continuously or through different speeds or whatnot. So that's a positional one. A continuous servo will you can tell it to turn in a particular direction at a particular speed, and it will just continue on turning. So there's no sort of start and stop or angular limitations that you can hit with that one, but you do control them slightly differently. So always try and check what sort of servo you're dealing with to make sure that you're telling it to do the right things and it acts how you expect. They have 3 connections: ground, power, so 5 volts, ground 5 volts, and the signal one. So there's actually a little chip inside a servo that does things based on the signal that we send it. And the signal that we send it is basically a pulse width modulated signal, which is like a square wave with various periodicity. And the qualities of that square wave tell the servo what to do. Luckily, we don't need to control the square wave directly. In Arduino, we can just say, go to angle 45 degrees or go to angle 90 degrees, and it will do that. So let's get this hooked up. Ground to ground. Power to 5 volts, so ground rail and 5 volt rail. And then signal needs to be driven by a pulse width modulation pin. So have a look at the digital pin options on the Arduino. You can see 0 through 13, but also some of them have this little, excuse me, have the little tilde symbol next to it, the little squiggle symbol. And that's also true of the physical Arduino. It's got the little tilde symbol next to some of them. And those pins that have that symbol mean it's a pulse width modulatable output pin. So we need to make sure we select one of those for to drive the servo. I'm going to choose pin 6 here. Doesn't matter which one, as long as it's got that little twiddle symbol next to it. And that means that we can do more than just write it low or write it high. We can write it to a certain value of that corresponds to the pulse width modulation. So there's our servo hookup. That's all we need for the physical connection. Everything else is in software. So let's go and have a look at that. We need to include a servo library. Okay, so Arduino's got a bunch of libraries that can, someone's done all the hard work of writing code for us and makes interacting with these servos quite easy, which is lucky because otherwise there'd be a lot more for us to write. So to include a servo library is like this line on number 3 here. So include servo.h in these little angle brackets. We'll go back to our code in Tinkercad. Include capital servo.h. And then we need to instantiate the servo variable, or the myServo variable, and it has type servo. So this type of capital S servo we didn't have access to it before, but by including the servo library, we now have access to that class of object. So just like that, we need to put it in. Servo, and it's called myServo. Okay. We need one more initialized variable for angle, which is an integer. So remember we talked about the angle of the position of this servo. So that's going to be that one. Anything else here? Yep, so we need to attach the servo to whatever pin we chose. So we could define the pin up here and then use that definition down here like we did for the LED and the button, or we can we know it's going to be attached to pin 5, so we can attach that down here. So that's basically saying we've got a servo attached to the signal pin number 5. For me, I did number 6 by the look of it. So I need to attach mine to pin 6. So myServo dot attach, oops, 6. Okie dokie. And then basically, we're just going to follow on. I don't recall exactly what this does. You can see what's new. We're reading the pot value, button state, and then we are mapping the pot value to a angular position. Okay, so we'll talk about the map function. We'll just get it down in a second. So angle equals map value 1023, blah, 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 blah. Angle equals map pot value 1023, 0 to 0 and 179. Anything else? Yes. So we compute a value for the angle, and then we actually tell the servo to go to that value. So which is done by myServo.write to angle. myServo write angle. Okay, start up the simulation. I'm assuming I'll probably have some errors somewhere, or maybe not. Cool, so it agreed with what I did then. Let's have a look at what's going on. Okay, so as I turn the potentiometer, you can see that the angular position of my servo also changes. Okay, so that seems like it's working correctly. Let's just go back to the code and have a look what's going on. Or if someone's feeling brave, they can have a think about what might be going on, and if they want to explain it, please speak up. I'd be happy for you too. Okay, so much the same as before, we're reading in the value from the potentiometer into pin A0, which is being read into this variable called pot value, which is an integer. And it lies between the value of 0 and 1023. Our button still works for our LED. As we can see, it's turning on and off, which is handled by this part of the code here. Let's have a look what's going on with our angle stuff. So the map function, you can read about it. So as with any of this stuff, you'll need to be doing plenty of Googling. you know, both in your own time and on Thursday to figure out what's going on and how to use certain things. So you can always look up the help for that particular function, but map is like a linear scaling. It takes the value of pot value and says, okay, well, it's gonna take the interval of 0 to 1023 and squish that down between 0 and 179. And depending on where the pot value lies on the first range, 0 to 1023, scale that appropriately so it now lies between 0 and 179. So 0 and 179, you should think about as being the angle of the servo. So angle of 0 to 180, we're using 179 because the servo can't actually go to 180. But that value gets returned in this angle variable. And then we're writing that angle and telling the servo to go to that position. So I'm just gonna stop that for a second and also just add in a new debug statement so it can help me. So as well as my sensor value, I'm gonna also write my servo angle is going to be angle. So you can use the serial monitor to get some insight into what's going on in the values in your code, which can be very handy. So let's turn this down to 0 and see what's going on. Okay, so when my sensor value is 0, my servo angle is 179. So that's why we did the 1023 first here. If I change this to go 0, nope. If I change it to be, instead of 1023 to 0, I reverse those and go 0 to 1023. That's going to be reversed. So 0 gets mapped to 0. And then as I wind up my servo, wind up the potentiometer, 1023 gets mapped to 179. So that angle on the servo. And anywhere in between that. So hopefully you understand what the map function is doing and how that's allowing us to take a value that's between 0 and 1023 and squish that down onto the interval of 0 to 179. But that can be sort of anything you like. You can, you know, not just use for this. The map will work in any interval to any interval. Good. Any questions about servo motors or serial monitoring? All right, the last half an hour, we will crash through some of the bits of 202. As I said, I want to focus more on the motor side of things. And yeah, we'll see how we go. I think we're relatively on track. Maybe I'll talk a little bit about project structuring towards the end for maybe 10 minutes or so. But yeah, not too much, I think. Yeah, we'll see if anyone joins in for that last little bit, but yeah, should be okay. Okay, so 202 focuses around the use of the ultrasonic sensor and a servo motor. We're up to speed with the servo, and what I want to talk about is something called a shield. So in this case, a motor shield. Sometimes they're called hats as well. So this bit of blue here is slightly different. Looks the same as my Arduino, this guy here, but don't be fooled. So this is the Arduino. This one here is the motor shield. So basically, Arduino is good at doing some things, but it's got a lot of capabilities, but not everything can fit on one chip, and we don't use it all the time. So the idea of shields is that we can get different functionality for fit-for-purpose things. So this is a motor shield, which means that it's good at driving various motors. And what we do for that one is it actually sits physically on top of the Arduino, and it's got header pins which line up with the headers on the Arduino itself. So it physically sits and we push the pins in between those. Like that, and it sort of sits as one unit. And the motor shield is great at driving different types of motors. So you can control, what do we got here? 1, 2 servos, as well as it also exposes the other regular GPIO pins for the Arduino as well. So we're not just limited to the 2 servos that it gives, although we can plug directly into these, but we also have access to the other pins. The other thing that it does is we can drive DC motors. So I don't have any here, but the DC motors that we have access to both from our own Nux store and as well as some salvage stuff from the e-waste. You can drive them using these. So basically forward and reverse at different speeds. And the other type of motor it can drive is a stepper motor. And a stepper motor can basically, it's not just like a regular motor that just spins forward or reverse and we just sort of set a voltage to it and it just spins. A stepper motor, you have a bit more finer control over what position it goes to it. So it's sort of like a servo, but where we deal in terms of steps. So we say take steps, 5 steps forward or 5 steps backwards. So that's, we're pulling a lot of those out of printers and scanners, which control the position of the print head or control the position of the scan head to basically, follow along to a specific point. And they can all be driven by use of the motor drivers on here. So what I'll probably do, I don't have access to the resources, we don't use the steppers that much in our Arduino stuff. But I might try and put some resources for the stepper motors together for Thursday, because it looks like we're going to have a lot of those to play with. I think, let's just have a quick look back at 202. Yeah, it's probably... sure whether it's going to be worth going through the task from 202, and they've taken away all my other goodies, so there's not too much I can show here either. Let's see if they've got, do they have any shields? Oops. I must be hitting the rotate button. I am. That's how my thing got rotated before. There we go. Motor. Yeah, so there could be some of these to play around with. You can see what happens when you apply a voltage to a motor. We could just put that to 5 volts. And see what happens. So I recommend that you have a play around with this stuff. If I run that, you can see that it is at 5 volts. It's running at a certain speed in a certain direction. If I reverse those and put in reverse polarity, it should run in the opposite direction. Yep. So we've got these exact motors here. You will be interfacing with them through a motor shield in the most case. So something like this, Pololu Simple Motor Controller. Let's have a little look at that.
Jonathan, you're not showing your screen.
Oh, thank you for that. Indeed, I'm not. Shit. Okay. So yeah, sorry, I was playing around with the this yellow hobby gear motor here. I'll just do that again. So if I hook up the terminals to, oops, oh, that circuit cannot be simulated. Well, why not? Can I delete that? Yes. So yeah, I was hooking up the hobby gear motor to ground and 5 volts. This is switched in terms of the polarity, so it's got a negative sign there. But I could switch that back over to, yeah, not like that. Grab that, and put it like that. And you can see that it spins in a certain direction like that. Why do they include this if I can't actually do anything with it? It's very annoying. I'll put a, yeah, it's got a few things here, but I can't actually, don't know if I can actually, where else do we have? So yeah, this is probably not too much use for this stuff. Yeah, because it's not the ones that we have. Yeah. But yeah, effectively you would be controlling these motors through the motor shield. This was called the Adafruit Motor Shield V2.3. And it's got provision for 2 stepper motors, 4 DC motors, with 3 amp maximum capability. And you can hook those up to different voltages as well. So yeah, I would suggest, if you're feeling brave, to follow through and do the 202 exercises. So I'm not going to go through them now. You can basically follow along. These guides are suitable for self-learning. So follow through 202. There may be a few typos in them. Usually we just address them on the day, so that'll be a good debugging experience for you. And yeah, Google away, because there's going to be a lot of stuff you'll probably want to do or want to try and do, but you won't know exactly how to do it. So have a Google and see if you can figure it out. And Tinkercad's great. You can play around with some of these. So DC motor with encoders, you can try and play around with those. They'll probably be similar to the sort of stuff that we have on the day. I don't know whether we have steppers specifically in here. Yeah, no. So you would have to have a look and see what the this particular DC motor with encoder does and what the pins do. But that'll be similar to the stepper in some ways, and I'll try and get some information packs together to use the steppers with what we've got going on for Thursday. Okay. So I'm thinking of probably finishing up the Arduino portion. Did anyone have any specific questions? A lot of this stuff is just learning by doing, so definitely get stuck into Tinkercad and playing with some of those components. You know, as I said, we've got lots of motors, belt drives, gearing, things like that, salvaged from the printers. So yeah, getting up to speed with some motors and whatnot will be pretty handy. And have a think about what sort of project you might want to be doing. You know, starting to map things out, and that'll be good. Any questions? Okay, Haflan, you potentially joined after I shared those links, so I'll reshare them. Yeah, so there's slides and PDFs there. I was working from the PDFs. I think there are some differences between the PDF and the slides, but yeah, have a look at all of them if you can. There's little nuggets of information in each, and that should help you. Yeah, get a feel for the sort of stuff that you can use the Arduino for, and the motor shield as well. So don't forget, for the judging on the day, we're going to be talking about not just the final product. We're going to be talking about things like the planning process, how well it was planned, how well you're working with your teammates, how well, you know, aesthetically, what's going on, if it's well presented. You're going to have to do a presentation to people to show them what you've done, and so how well you present. So it's not just the final product of what you make. We'll be having a look at the whole process and yeah, sort of judging off that. All right. One other thing that I will say in terms of project planning, I think we'll probably give you a bunch of like butcher's paper or something like that to scope some ideas out on. And I like to, you know, obviously the brainstorming process is super powerful for things like this. You know, sketching things out on paper, and also particularly with Arduinos and things that have a software component, pseudocode is an excellent way to sort of brainstorm and go from that, oh, I've got this idea of what I want to do, but how do I make it reality? So if you haven't done pseudocode before, you're just basically writing out in a algorithmic-like fashion the sort of steps that you want to do, and in the context of Arduino, particularly what we want to do in that loop function. So whatever that function is, that's just repeating over and over and over again. You want to think about, well, what's my invention or project doing that it loops, and how does that get handled every time it goes around? And just writing things out in basic forms like, you know, move motor forward 10 steps, pause for 10 seconds, you know, turn a light on, then turn a light off. So thinking about that in terms of pseudocode can be super powerful and will help to streamline the development process. Yeah. Okay, I think that's all I've got for you guys.
Do you know how many teams there are approximately?
How many teams? I think probably 10 to 15. We're still finalizing the team assignment and numbers, but that's what we're looking like, about 10 to 15 teams of 3 to 5 per team.
And then will everyone just be working in the workshop there, like in that space?
Yeah. So the space will be set up for probably like a table per team. Obviously it's a reasonably long day, so you can come and go as you need to. Once you get inducted, bring your student cards because you will have be granted swipe access to the general utility space of the creator space. So yeah, once you're in and have been inducted, you can basically you know, walk around, come and go as you need to. We'll all be working in the one space. You'll have access to your basic tools, you know, like basic electronics, like wire cutters and things, and power supplies, function generators, oscilloscopes. You'll be inducted on basic hand tools. You'll have access to all the materials supply of the space. So I think they provide some basic wood, like pine and MDF and things like that for realizing the physical parts of your designs. You know, hammers and saws and whatnot, you'll have access to. So yeah, basically whatever general access to the creator space is allowable from the general induction.
Thanks.
No trouble. All right. Well, thanks for joining, everyone. Hopefully that's been enlightening in some way. It is a crash course, so you'll probably want to go and do some of your own tinkering on Tinkercad, researching of components and things like that. And yeah, ready and raring for Thursday. Looking forward to it. Thanks a lot, everyone. I'll see you later.
Yeah, thanks a lot for the session.
Thank you.
Thank you, Jonathan.
Oh yeah, Jonathan. About the induction. Do we just attend the general induction one, or do we also need to do the induction from the creator space?
Good question. Let me double check with Alex. I know most of it will just be able to be organized on the day, but let me double check if there's anything you need to do prior to that. Just 1 second. Great question.
Today, obviously, I can't do it today.
Yeah.
But tomorrow, there is still capacity in those sessions. So if I can get to one of those.
Yeah. Okay. So is it just the general induction?
General and intro to electronics, but they should be running sequentially.
Okay.
So if you come in for a general one, the intro to electronics should be.
Okay. Chills.
Oh, but the other thing is, if they have already done their general induction, then we will be running a special intro to electronics for them on Thursday.
Okay, but only intro to electronics.
That's the only induction we're
Yeah.
running on Thursday.
Is there capacity on that, or just whoever's here can do it?
I mean, we've got a maximum number, I think 16.
Yeah.
We also said if emergency situation and there's a whole bunch of people that don't have induction, we'll send one person per group to get inducted.
Yep.
And then they can be the ones that just deal with all the.
Okay. All right. Yeah, we might want to do a push around making sure people have done inductions. Yeah. Okay. All right, guys. So yeah, I've just confirmed the situation with inductions. So the deal is there should have been an email sent around to make sure that the idea is that you need to get the induction, the general induction, and preferably the introduction to electronics induction done in your own time prior to the hackathon on Thursday. So obviously today, if you haven't done your general inductions yet, I'd suggest you jump on to the eLearn training stuff, because there's an online component and then you need to book in for an in-person session. And at that stage, that'll be tomorrow, will be the chance to get that done and knocked off. So I've heard word that there is still capacity at the moment. So if you haven't got your general induction sorted, jump on and get that sorted for tomorrow, and that's going to make Thursday go a lot smoother. So there is a reasonable bit of overhead in doing the inductions, in terms of the general inductions, about 30 minutes online component, and then about an hour and a half of your time in person to do the induction. And yeah, the idea is that that's all sorted out before Thursday, so we can come in and get started as cleanly as possible. There will be a backup plan if there's a lot of people who haven't been inducted on Thursday, but that's not the primary goal. So if you can, and if you haven't done already, jump on to the Creator Space website now and get cracking on those inductions, because that'll make Thursday go a whole lot smoother.
All right, thanks, John.
No problem. All right. If there's no other questions, I'll see you guys later. Thanks for joining.
Thank
Thank
you.
you.